So I'm an assistant professor in School of Architecture and affiliated with FIU Institute of Environment, and I'm trained as an architect with focus on urban design in my undergrad. I focused on computational design in my graduate studies. However, for my PhD studies, I was not able to find certain conversations about importance of storytelling, importance of data-driven workflows, and interdisciplinary research in the schools of architecture that I was looking at for my PhD. So therefore, I found a program in School of Cinematic Arts across campus from where I was teaching and began a journey there, which led me here. So interdisciplinary research has been quite important to my background and some of the work that we're also doing here in FIU School of Architecture.
So interdisciplinarity is also a major theme of my own academic career. I began in sociology with a liberal arts degree, went on to get a master's degree at University of Florida, and currently pursuing my PhD in design at University of Genoa in Genoa, Italy, with a focus on robotic 3D printing for marine construction. My background, my first career, I'm a transitional career academic. My first career was as a carpenter. I worked as a builder for 15 years before coming into architecture. And so I think for me, this idea of interdisciplinarity is also really, really strong. I feel like somehow I get a little bit pigeonholed in kind of technology side of things, but my foundation is pretty firmly in the liberal arts. So I find interdisciplinary research and working with colleagues across disciplines is really important.
So we want to start off by the first keynote speaker. So our first keynote speaker, James Murley, gave you an overview of Miami's resiliency efforts and also some of the challenges that the city, but also the state is facing. And one of the things that really stuck out from that keynote conversation for me, and probably this is not a news to any of us, was the fact that he was mentioning how about 10 years ago, even mentioning terms sustainability or sustainable design or climate change was a big no-no in conversation, especially with policymakers and people that really facilitate a lot of the funding for research or create support for universities, for centers to go forward. And the fact that, in a sense, we are making progress by at least being able to call it what it is in some sense. But then he focused on the fact that there is a disconnect between us designers, maybe thinkers, and then policymakers. And this is not a news, right? This has always been, unfortunately, the case in the work that often we're doing. So in a sense, some of the conversations we've overheard throughout the papers and with even side conversation is the challenges that some of you are facing when you're trying to perhaps do work that's going beyond the scope. Now, this is technology-wise or funding-wise outside of your department. So we thought that for maybe a conversation of today, we can maybe discuss a little bit what the challenges and maybe the approach that we have here, and then start to see if we can see some similarities and differences. So for instance, at FIU, Institute of Environment has been a central, let's say, a pivot for a lot of the research that's happening across campus. That's one of the reasons that, along with, let's say, the efforts of School of Architecture, it drove me to move to Miami to work with this interdisciplinary center. But it's not that easy. Although there's funding, although there's already existing conversations that's been set up by visionaries, institutional visionaries, and has taken years to set up, it's still quite difficult when we as architects, as designers, as let's say urban planners, we are sit across table with scientists, from environmental scientists, material scientists, And it becomes a challenge when we're beginning to talk about funding opportunities. It seems like we can collaborate, but it's quite difficult to lead these efforts. And also when it comes to seeking resources, there's a negotiation. And what we have leveraged here with the robotics and digital fabrication lab, we've leveraged space for certain type of knowledge, for certain type of funding. And one other effort that we've done, we've understood that, let's say, every engineering course, whether it's electrical engineering, computer science, has a capstone course, and we've approached the faculty and the department heads to begin to mentor electrical engineering, computer science engineering capstone students, and begin to create a working relationship with our students. And this has taken years to begin these conversations for us to begin to create hardware and software components that then could allow us to rethink future of built environment, future of data collection, future of information visualization, robotics construction, etc.
So both Biane and I are currently have mentored a dozen or more teams of students who are developing instrumentation for collecting environmental data that can then be used for visualization purposes that eventually can be rolled into policy changes, but at the moment is sort of in the area of pure research, data collection and data analysis. I'm working with students to actually develop tools specifically for our laboratory. So we're developing end effectors for robots and working with computer scientists to develop software for controlling onboard tools for robotic instruments. So those are some of the kind of small scale things that we're doing working with students. In large scale projects, we have the org chart up here for Robotics Academy, which is our latest major grant funded project. And as you can see from the chart, we have people from a broad spectrum of different disciplines, many of us from architecture, but really working with computer science and engineering faculty, as well as professionals in the field to help support a research agenda that looks at education as a primary focus.
But this is by no means unique, and I'm pretty sure that you're doing similar efforts and you have perhaps more complex charts to then rethink collaboration within your departments. So if we maybe take this idea that for advancing research, seeking funding and sharing resources, interdisciplinary collaboration is encouraged. But I think, at least from our experience, it hasn't been easy. Sometimes we really need to earn our seat in these conversations. We really need to prove technical skills in order for scientists or other disciplines to begin to trust us. So we want to hear from you. What are some of the challenges that perhaps you faced in order to successfully lead or engage with interdisciplinary research?
Maybe a first, like, really easy opening question: who's doing interdisciplinary research? Yeah. Okay. Excellent. All right. And what are the challenges that you're facing? Just go ahead and shout it out.
I can share something, and I think this from the perspective of someone that is also pretty new. So it's both challenges with the entering decision and also with the type of engagement transdisciplinary research. I would say that the first challenge is to, I think the department we have to see the importance of that beyond the paper. I think everybody agrees on the importance of doing transdisciplinary research. But at the moment that you mentioned that we need to create a space for a biolab or a wet lab, things start to change and perceptions start to change. So creating this awareness and the importance of what are the specific equipment needs and funding needs, that is something that I identify as a challenge. And it relates to what you were saying about how to apply funds, how to be able to sometimes be strategic about where do you think the agency funds would be more open to this type of research. Something that I also find challenging is time. You need to be very patient. You need to build these relationships. Sometimes you need to start from a very casual point of view, I would say, not asking anything, just trying to, I don't know, have a sense of where the interest of other researchers might be and how to connect with them. And what I think is not a challenge, but it's something that I find very, very useful, very helpful is students' involvement. The moment that you get the attention of the students, things start to become much easier, and immediately faculty members, the hierarchy starts to play more. So yeah, that's
Okay. Yeah.
A big challenge for us too is continued interest. Is try, like we get all these people on board and they're all excited about this project, and then you start working on it and everything kind of slows down and people start kind of falling away and not being as involved. I think our big struggle too is the whole kind of continue, everybody's still working on it, even when it seems like we put to the side a little bit. That's been kind of our biggest struggle, is because we do have a lot of student involvement currently because we're just launching a new institute. So we're kind of really utilizing student involvement, but it's kind of the time struggle and the continued.
So one of the things that that I found particularly gratifying with the first paper that was presented in the technology section, technology sessions, was Tristan Al-Haddad presented a project that involved undergraduate researchers, graduate researchers. It was interdisciplinary. It was multi-institutional, and also involved institutions in Republic of Ireland and Northern Ireland, which is super, super exciting. I think that the next topic we want to take a look at here is what's alluded to in the previous comment about technology access. And that's one of the things that's really, really challenging for conducting some of this research. Access to labs, to build a lab, powerful data processing, access to computing time, visualization technology, which can be prohibitively expensive, and high-tech fabrication tools. A lot of those are prerequisites for conducting cutting-edge research, and it's not always easy to gain access to some of that technology, but B, build the institutional foundation for being able to utilize that. It's great to be able to have a lab if we don't have staff or funding to support expertise in that area. It's really, really challenging to make significant progress. So what kinds of issues are you experiencing in relation to those issues of access to technology and
the research gap and biases that it could create, right? Let's say if we're talking about robotics, there's only certain institutions that are able to access, let's say, the latest and different types of machines. And actually, our keynote speaker will present some of the wonderful research that they're doing in ETH Zurich. And ETH Zurich is a university extremely well equipped with the latest technology. So we're wondering if we could share maybe a couple of thoughts about your maybe thinking regarding technology access and relationship of that to interdisciplinary research.
My research, the research itself requires the development of existing machinery, and what is difficult is that while I'm working on finding a solution to process materials and recycling them, there's also a need to develop these machines, and I'm an architect, and I need strong engineering background to do that. So I think it's rather the communication that is a big gap, because I can't really explain what I need. I can explain what I aim for, and then they have to figure it out how to create a that can be I think it's rather the inventive part of it that is always a big step.
Yes.
Yeah, I think especially with visualization technologies, it's also at ARCC at our university, it's both top down and bottom up. So you have to have a thing, get this straight on. If you have to found problems, it's just finding mistakes for you. Even though it's virtual, so requires to still have to concentrate for mistakes from the first few. But as far as like funding goes, and things like that, that's a good way to technology. Yes, they can be complicated, but there's a lot of funding out there for that.
Mhm.
So I think it's just being proactive about it. It's pretty easy to get along.
Right. So perhaps partially this is a funding issue and maybe asking the right questions or right collaborations, but also looking for the right places. So there will be a workshop later today about National Science Foundation maybe approaches led by Professor Shang, who's leading a lot of the interdisciplinary collaborations here. And I want to also mention one other component, which is perhaps our maybe approach to tools and tool making. So there's a kind of conversations about space, there's conversations about maybe hardware and technology that has to be acquired, but there's also maybe an approach to maybe are thinking about technology. So for instance, we know that accessibility to tools, it is quite important, and not maybe for even a research lab, but for our students. So then starting to think about ways that open source perhaps approaches could be introduced to tool making, but also tool dissemination and teaching is quite important. And perhaps with that, I want to segue into our wonderful keynote speaker today, who briefly, hopefully, will mention some of the wonderful work that the Block Research Group has done over the years in terms of developing open source software and dissemination efforts. So I'm extremely honored to introduce Professor Dr. Philippe Bloch, who will be presenting a keynote lecture today on the topic of disrupting concrete construction. Philippe Bloch is a professor at the Institute of Technology in Architecture at ETH Zurich, where he co-directs the Block Research Group. Together with Dr. Tom van Melle, he's the director of the Swiss National Center for Competence in Research, or NCCR, in digital fabrication, and founding partner of Oxendorf, de Jong, and Bloch. Bloch studied architecture and structural engineering at the VUE in Belgium and at MIT, where he earned his PhD in 2009. Research at the BRG focuses on computational form finding, optimization, and construction of curved surface structures, specializing in unreinforced masonry vaults and concrete shells. Within the NCCR Block Research Group, researchers develop innovative structural informed bespoke prefabrication strategies and novel construction paradigms employing digital fabrication. With the Block Research Group and Oxendorf, de Jong, Bloch Engineering, Philippe Bloch applies his research into practice on the structural assessment of historic monuments in unreinforced masonry and the design and engineering of novel shell structures. I'm extremely honored to introduce Philippe Bloch as a keynote today, and looking forward to seeing your presentation. Give me a moment.
Thanks a lot for the very nice introduction. Thanks also for the invitation. I'm excited to present what we're doing. Let me try to do this smoothly. Do you see my screen? Can you see my screen? Should I go ahead?
Yeah.
Yes, okay. Yeah, so disrupting, rethinking concrete construction in a context of sustainability, ecological pressures. I chose this title on purpose to provoke a bit and to hopefully at the end we can have a bit of a more nuanced discourse about sustainability than the current material-driven black and white thinking that is often happening. I hope, I expect that I'm preaching to the choir. We all know that we will have quite a significant population increase that is estimated, expected in the next 20, 30 years. We also know calculations like these, that in order to provide adequate housing and infrastructure for all these additional people, we will have to build the equivalent of one New York City every month for the next 40 years. I hope we don't do it like this, particularly because globally, our industry, and when I say our industry, I'm talking about both construction in general and the building industry. We are globally responsible for 40% of the man-made greenhouse gas emissions, 40% of use of virgin materials or resources, and we are huge waste producers as well. So I hope with these few slides, and again, I do hope that I'm preaching to the choir. I hope that you agree with me that we have to change both the way we design, but also how we build our structures. As a structural engineer, a structural designer, so half architect, half engineer, I will be focusing mainly on the embodied emissions. So those are the ones related to everything that happens before you turn the key and you start operating a building. So the impact of materials, of transport, of construction, and so on. One of the reasons that I'm excited to be in this field also is because actually we might, maybe cheekily, but we do have a theoretical solution to address the operational emissions by just switching. If we would do this at a global scale, then we kind of have a solution. We can go for renewable green sources of energy. We don't have such a one solution fits all kind of strategy for the embodied emissions. What matters in embodied emissions, I borrow this equation, and it will be the only equation that I will be using here by Catherine de Wolf. The embodied emissions can be translated in the global warming potential of a building. And why I like to bring in this equation is because it shows immediately what really matters. That you basically want to take all the parts of a building and the impact of that building will then be proportional to the mass of material used, the M, multiplied with the embodied carbon coefficient. So these can be looked up for different contexts for different materials. So these are numbers that give you an estimation of the emissions of the carbon footprint of a material. And then last but not least, very important is you want to divide this over the lifespan of your building, ideally. But this is also an opportunity to add some circularity, some circular thinking in there, because through those attitudes, and I will talk about this in more length through applications and examples, you want to try to keep resources, components, and indeed, ideally, your building as long in the loop, in the circle as possible. So why I put this equation is because we need to get away from a discourse that says wood is good, concrete is bad. I don't know to what extent that is relevant in your context, but in Europe, this concrete shaming and greenwashing with wood, with timber construction is absolutely happening. And this equation very clearly shows that that is very narrow scope and that it's not just about the materials, the ECCs, it's also about the mass, and it's about understanding a material in its context, in its full life cycle of a material, of a building, and so on. And so I will highlight this a bit further along. Our group proposes a solution. We need many solutions to do better, but we introduce two themes or two concepts: strength through geometry and material effectiveness. So I already made some comments, and so you see that I don't use the term material efficiency, which is in the historical lighter is better kind of strategy, because it's not just lightness that matters, it's also what you do with the materials indeed. So let's first look at strength through geometry, and I will use 5 projects that we have done to highlight some potentials and some different aspects that really could offer some outlooks. I start with the Armadillo vault that we built for the 2016 Venice Biennale. What you're looking at is a cut stone vault with 399 pieces of cut stone that are held together without any glue, without any mortar, without any reinforcement. So this is really structural geometry, good structural form. This is gravity and historic principles that hold this together. Indeed, the reference for this kind of project, was, of course, my original research focus on understanding why these beautiful structures, here the fan vaults at King's College at the University of Cambridge, why they're standing still after 500 years. And so the more I studied those, the more I realized that in modern design and engineering, we might have forgotten some essential principles that indeed allow these unreinforced vaults to be perfectly safe still after centuries, even though they have a thickness to span ratio proportionally as thin as an eggshell. So we have been developing a lot of tools to rediscover, to look at these geometries. This is, for example, Rhino Vault, which we showed very early on, which is used by many practitioners and students alike. But we did this statement at the Biennale because you can do anything on the computer. And so we really wanted to shake the community. And here you see, by the way, our colleagues of the Escobedo group out of Austin, Texas, assembling this stone vault indeed without any connection, just dry assembly indeed. So here you see some additional images. It is still in boxes. There is some rumors that it might be finally installed for its final resting place, I guess, but let's see if that goes forward. But what I wanted to show with this project, so again, looking at this very thin sheet of a very humble, simple, traditional material, what you can achieve when you get the geometry right. So the first lesson, or the first lesson is too arrogant, but the first thing I want to say is, if you get the geometry right, if you reintroduce these first principles of vaulted traditional geometry, then you can significantly reduce the volume of your structure, so the mass. So as you remember, an important part in that equation. A second aspect about strength through geometry I want to show through this project, the Mapungubwe Interpretive Center by Peter Rich Architects, John Oxendorf, Michael Ramage, but I was lucky to be involved in the safety assessment of the engineering of the vaults that were built. So this is in a very remote site, a soil press tile, so vaulted geometry tile vaulting. The reference here are these beautiful tile vaults by the Guastavinos, for example, here in the Oyster Bar in Grand Central Terminal in New York City. So what you're looking at is not decoration. It's one of 3 layers of unreinforced masonry of tiles that were layered without the need of a scaffolding, without the need of, well, scaffolding, yes, to work, but no formwork needed. So this was great to introduce this in a context where materials are expensive, where you had to bring in everything. So all the timber that you see there is not to support, it's not a formwork, but is actually to guide these until 1-2 weeks before unskilled laborers to basically trace this funicular, this compression-only geometry. So here you see some first successes. But the reason that I show you this project is because it was driven by using local resources in all aspects. So the local communities, but also local materials. So here you see on the left, the soil being compressed with just a little bit of cement, 7% of cement, to make these tiles that then could be assembled. But the message that I want to give with this project is basically captured in these 2 pictures. On the right, you see that these women are carrying the tiles in small packages. And the reason for this is that these tiles are designed to only take a little bit in compression, 2 megapascals, which is 10 to 15 times less than a standard concrete we use. But if you take one of these tiles, then you can just break it in bending. So, but on the left, and that is where it gets exciting, if you place those so-called weak non-structural materials where the forces want to flow in compression, this becomes a totally safe structure, as indeed has been done in historic vernacular construction. So what's happening here is that we have an arch, but an arch is only good for a certain loading case that you design it for. You also need live loads. So the red line represents where the forces might want to travel in compression. And so you see that in this case, with the thin arch, we don't have a path to safely bring these forces to the support through compression only. So we added some stiffeners. And if you then add a tension tie, what I just did with you in the last 10, 15 seconds is we basically reintroduced an alternative to our typical reinforced concrete beam or floor plate, but one that uses 70% less volume, right? So this is actually exciting. There is no computation, there is no kind of complexity here. It's reintroducing common principles that we are no longer using. And in our context, obviously, I think this number speaks for itself why that is relevant. So this was a nice case study early on in 2008. This was constructed. So this weak material is still the permanent structure for this museum building. So the second aspect that I wanted to show is that, or to highlight, is that if you get the geometry right, so if you get strength through geometry, then you can also significantly, on top of reducing the volume, so the mass, you can also significantly reduce the emissions of the material. And why I can say that is because we can activate low strength material to be safely structural, and there is almost a one-to-one relationship between how strong a material is, so its material strength, and how polluting, so how much it emits, what its carbon footprint is. So here, by just having these local sources, this of course offsets the impact again significantly. So the second part, the ECC, the embodied carbon coefficients in our equation. Of course, this we did in a context where we need to challenge the status quo. So this is a picture I took myself of low-cost housing developments in Addis Ababa by the government. And so I don't have to say much, but you see multiple challenges in just trying to mimic how we used to build, or how we have been building irresponsibly in the global north or the west. A next project that I want to show is one of the latest that we have done. So striatus, which was a collaboration with Zayed Architects and Incremental 3D. We just dismantled it. It was there for more than half a year at the Venice Biennale this year. What you're looking at is a masonry bridge, an unreinforced masonry bridge, where all the elements are not cut stone or cast, but are directly 3D printed, concrete 3D printed. So what we wanted to demonstrate here in this project is a continuation of this strength through geometry argument, but then translating this to a material system and a new technology that is totally en vogue and where everyone seems to be pouring their money and their hopes in. But we wanted to show, if you indeed treat the material for what it wants to be, I would say concrete is an artificial stone. An artificial stone is happy in compression. So if you can generate systems that really understand the limitations that we translate into opportunities of the material, then you can get to a next level of efficiency indeed. So when I say about masonry, so the masonry connection, we have masonry logic on two levels. So globally, the bridge is discretized like a Roman arch. But then also on the level of the elements, of the voussoirs, of the blocks, all the print layers, all the concrete 3D printed layers are perfectly orthogonal to the dominant force flow within the structure. And that allows us, you will see this later, to really achieve a next level of efficiency. So from the beginning, we used our typical masonry kind of strategies to discover geometries that would be suitable. But then on the level of the elements, it was important to use more advanced concrete 3D printing, which is called this 2-component 3D printing, which allows you, as you can see here, to not have just a simple extrusion, horizontal extrusion, but an inclined layer printing, so that you basically can indeed align your forces to your print layers to the forces in the system. I don't have time to expand on this too much, but the trick behind all of this is that rather than what typically is being done, that we design a geometry, then we discretize it, and then we try to see if it works. This process actually started entirely the other way around. And this is the work of Shajay Bhushan, his PhD. In our case, we basically encode all the fabrication constraints, all the structural logics, both locally and globally, are encoded in the print paths. So that means that we continuously treat the print path explicitly, and so geometry is implicit. But of course, we need to also have strategies to have a global control. But this is a key thing that in this project, very clearly and very extremely, we set up a custom design framework that allows to embed all this knowledge in every single design iteration that we generated as a collaborative team among all the different partners. So, but the key point, though, what I wanted to show is that I do see an outlook of an appropriate use of concrete 3D printing. Appropriate in the sense that we use this new technology to really actually offer the concrete material to work as it wants to be used as a masonry system. And so you see that this offers on the left is synthetic stone in a way that is hollowed out, where material is only placed where relevant. And on the right, again, this alignment to a 3D flow of forces, which allows us to not only globally be unreinforced and dry assembled, but also globally, we don't have any reinforcement in the 3D printed concrete. So there is no fibers, there is no embedded layers and so on. So this structure was safely designed using a combination of high-tech opportunities, so the promises of 3D printing, and then historic principles behind it. Another thing which one has to highlight in this kind of in the argumentation of 3D printing is that the 53 stones of the bridge were a total printing time of 84 hours. So this is super exciting, because that meant that we could keep pushing the design engineering all the way until the final moment where we could just crank out all of these elements. That none of them failed, because, as I said, the long time kind of experimentation and coordination between all the computational pipelines allowed us to fully understand what the constraints of this 3D printed material had to be. I want to give you maybe one insight, because I talk a lot about the bigger picture sustainability targets that we want to achieve, but there's also some nice kind of digital fabrication aspects that perhaps are interesting in this project. For example, globally, you have a beautiful compressive forces throughout the structure that keep it stable, but locally you might have, if someone walks on it, you might have some local impact loads that are too much. And so in this case, for example, the 2.5 centimeters that we had in thickness of the printed kind of the printed layer was not sufficient to deal with these local impact loads. So that meant that we had to basically have the nozzle pass twice over the structure. And so you see that even though this is not part of the global geometry, in the middle, from a fabrication standpoint, you see that this changing of the nozzle then creates this very dominant feature. And that, as the design team was not kind of happy with this very pronounced feature. And so instead, basically, and we only needed a thickening on the top layer. So we decided to basically have this turning around happen at every single layer. So this is something that was a necessity or kind of a conclusion of fabrication. But then rather than just being frustrated by it, we took it as a design opportunity to then have aligned features that really also show are in line with the global force flow of the structure. And then, as said, because of the masonry logic, then we could simply kind of assemble it on site. I'll just actively say it before someone says like, yeah, you talk about sustainability. What is all this single-use timber that you're using there? This project took just a few months, a lot of stress. We were innovating on the material side, on the engineering side, on the generation and so on side. I'm already making excuses, but believe me, there was no more time to develop a fully reusable, demountable kind of a system. I hope you will accept my apologies that we ran out of time, but this for me is actually a no-brainer because you just need 3 points per piece. And so we can imagine that in the next iteration, which I'm very pleased to say that there will be a next iteration, in fact, a permanent structure, we will no longer, of course, use the single-use kind of timber formwork. So here you see, though, another advantage is that because we place material only where needed, these elements are very lightweight. So that allowed, on the left, 2 people from a professional crew, together with 2 people on my team. You see, by the way, on the right, that is Tom van Melen, the brain behind many of the things that we do. With him, I co-lead the group. So that only these 4 people, 2 non-experts and 2 experts, could assemble this bridge in just a couple of days. So here you see that we only needed a very simple, lightweight spider crane to assemble these elements, and they nicely, in a dry assembled kind of way, came together. So why was I excited about showing this bridge to the audience, to the Biennale crowd? Was because we achieved different aspects, in my opinion, that really could be a framework or an opportunity more globally than, of course, this funky structure that we built. I already emphasized quite a bit this reduce. We place material only where needed in the compressive forces. So not only globally, but also the section is optimized to only place material where needed. The aspect of repair has to do with the fact that we separate materials, plus we have this discrete assembly, so fully removable, dismountable assembly, which allows you to actually not, for example, and this in the US is a gigantic challenge and problem nowadays, is embedded reinforcement corrodes, and so what to do, how to deal with this aging infrastructure. So repair is perhaps for infrastructural projects not to be underestimated kind of aspect. But then the reuse aspect is also similarly related to that, because we have full demountability. We can actually start to imagine that we can reuse the components. Again, for this bridge, this might be a bit of a silly concept that we are moving this bridge around, but imagine more generally, and you will see how we use this in a much more pragmatic solution, more generally for prefabricated modular construction, that you already from the beginning have the opportunity to reuse properly all the components that you have. So for this, you indeed need connections that don't have a chemical bond, so you cannot glue them. You want to be able to easily remove them. And again, that's where the masonry principle allows us to have these self-registering, beautifully stable, reversible connections, right? And then the last point was directly relevant because this disciplined separation of material allowed this bridge to be very easily crushed, recycled with low energy associated to it. And it has been in Italy reintroduced into a new batch of concrete through upgraded construction demolition waste indeed. All right, so that's what we wanted to show in this bridge. So I'm happy that we managed to kind of share this bigger kind of points. But it was in this beautiful garden. Sadly, it's no longer there, so you can no longer go visit it. But that's why I bring you a few nice pictures by Studio Naro. Here on the left, you see these grooves, these features that were a fabrication necessity that we turned into a design opportunity. And yeah, it was great. It was every day at 5 o'clock, the entire neighborhood came around with the 20 add something, dogs that loved walking under it, peeing against it, jumping on it, and so on and so on. So this was a very beloved kind of object. Maybe here also a nice thing to show is because we have this global control, because we really control the print path from layer to layer, and we don't we can also control these kind of little defects. So these traces that you see on these edges is actually where the internal stiffener nudges the outside layer a little bit. And so basically, rather than again taking this as something that we need to fight, we take this as an aesthetic opportunity to give that additional kind of layer of legibility to the structure indeed. So here you see very clearly what I started with, this masonry on 2 levels, globally the discretization, as we've seen with with typical masonry, voussoir arches, like a Roman arch indeed, but then you also appreciate again this aligned layers to the global force flow. So the message in this project is some hints about how you can start to address this T, right? How you can start to design for future demountability, design for future recyclability. And this is essential because here with this unreinforced concrete, we have a pure material, a non-polluted material that can be easily recycled. And so that means that in the next batch of concrete, we no longer need to use virgin resources. We can use construction demolition waste going forward as an example. But I also gave, of course, the better option is to directly reuse your components. And this will be relevant in the future. As I said, it was very intense collaboration between our groups. I did Architects Code Group, then Incremental 3D were the digital crafts people, so the 3D printers out of Innsbruck, and then Holcim developed the specific concrete inks, and also made this project possible by backing it financially. But all of these different teams, all of these different innovations could not happen in parallel if we would not have from the beginning found a way to make sure that all of our knowledges, all of our experiences would come together. And that is where we have used in all aspects of this project, this open source computational framework, which we have developed already now. It's in development already for 5-6 years. It's now a full community-driven process. This is called Compass. All right, next project. It will sidetrack. It will be a small sidetrack, but I still find it an exciting project to show. But it shows something else. It shows the challenge and the potential opportunity of computational design and digital fabrication to address the fact that structural geometry is non-standard. And non-standard geometry is typically indeed much more expensive and difficult and wasteful to realize compared to, of course, our status quo, our polluting, problematic status quo of our straight beams, floor plates, and so on. So what we did with Netcandela, so it's already in the word, is we wanted to show the opportunities of a knitted formwork, so a 3D knitted formwork, and we wanted to kind of do this in the context of the famous shell builder Felix Candela. So Felix Candela did these amazing shells, very efficient, high-power shells, and so on. So here with 30-meter spans with only 4 centimeters of reinforced concrete in thickness. But with these formworks, there was a lot of labor, a lot of resources kind of involved, even though he used high-power surfaces that allowed straight formwork elements that could be reused indeed. You still can imagine that these kind of formwork systems would be prohibitively too expensive and problematic in today's kind of context. But also modern design, modern surface structures in concrete deal with this challenge that you need that scaffold, that formwork that needs a foundation, all the renting of this formwork. You build a beautiful, super detailed timber structure that will only live 28 days until the concrete is ready, and then it turns into this. So that is what we have been challenging with projects like Netcandela, to challenge the traditional, in a way, brute force rigid formwork, where you need all that material, often single-use material, to keep your mold, your formwork to push against gravity. And on the right, and this is of course a bit of a caricature, but you see that a flexible formwork has the outlook to significantly reduce the foundations, the logistics, but then also of course the waste associated to realizing these very efficient structural forms. So here you see this knitted. So I'm talking literally about a sweater. So a sweater was used to shape this concrete shell. More specifically, there was a pre-stressed cable net, and then the sweater allowed it to basically to have a shuttering layer to where we could apply the concrete. So this was the PhD research of Mariana Popescu. She's now at TU Delft. And here you see this knitting machine. On the top right, you see Mariana knitting arguably the longest scarf in the world that could be very lightweight, vacuum packed, and then in 2 suitcases could be brought on site. What's exciting here, I will not focus too much on this project, but what is exciting is that the knit had multiple layers and came with all the features necessary to work with local crew. So with Mexican, so this was in Mexico City, with Mexican expert concrete finishers. They typically do kitchen tabletops and things like that. But here we basically offered with this simple knit, that was the logistical device that allowed basically to introduce this innovation, to literally give a more interesting kind of canvas to these workers locally. And you see here on the bottom, this was their choice, not to spray it on, but actually to do it with manual kind of finishes. And that was a nice success indeed. So this project used the knit as a stay-in-place formwork, so to also have a unique kind of permanent finish to the cold concrete shell on the outside. But here in the top view, you see how thin this structure indeed was. And what I didn't talk about is that it is actually a very thin shell with stiffness running in 2 directions. That is something that the knit also allowed us to realize efficiently on site. But perhaps here, because I make all of these statements, let's look at what these some numbers of this shell. So we are talking about 50 square meters or 5 tons of concrete. The total cost of the cable net, the connectors, the knit, so everything except for the reusable external formwork cost only 2,300 euros. And the total knit was only 25 kilograms, which indeed allowed it to be brought very simply on site. But what is exciting is that if you calculate, and there's references that we used for this, in order to generate a mold that would achieve the same geometry, we would be milling for 3 months non-stop. And so here then to see that the entire knit was cranked out in 36 hours, considering that from the very first email where Zahadit Architects invited me to collaborate to the opening of the exhibition, in that time frame, which is, by the way, only 3.5 months, we needed to develop the system, do all the design iterations, the engineering, the fabrication, and then, of course, the on-site construction with a construction crew we never worked with before. So I quickly translated this. So 500 square feet, $2,500 US, and 55 pounds. So those are some, I think, starting to be some convincing numbers indeed. But what is more convincing than sending 55 pounds to the building site is just sending data. These knitting machines, these are standard machines that are available anywhere. And so we can also, I don't want to overstate, but we can also start to imagine different ways, and we have to reflect what happens in prefab, what happens where, what happens on site. And we need to not only optimize the ecological aspects, but also rethink the processes and the efficiencies on site indeed. All right, so now the last project that I wanted to show is perhaps the first project, no, except for the South African one then, the first of my projects, which I'm very proud that will not be dismantled, demolished, or pushed until failure. It's a permanent structure, finally. So it is a unit on top of a building. It shouts loudly, so it looks very weird. So let's pay attention to it. Let's see what it has to say. So maybe the roof is already quite unique. You can see that it's a very thin shell. Well, you don't see that it's a thin shell, but it is a very thin shell that was built on flexible formwork. In this case, not stay in place, but we developed a kit of parts that allowed basically to be reused. And indeed, we used this kit of parts for 2 shells, the full-scale prototype and this one indeed. And then in this case, we used, again, a formwork, a fabric formwork to spray the concrete on that. So then we had this shell only on 5 points, up to building standards. We also had, in certain parts, a double layer shell to not have any thermal bridges and. This is a bit crazy. I mean, it addresses similar kind of things, but I don't want to linger too much, because basically what we wanted to do with this shell is to show that this is possible in time, on budget, with traditional partners, if you really approach this with a very coherent BIM on steroids, as one of our partners told us, through Compass. So everything in this project, all the coordination, all the new innovations was introduced in this real-life projects through this open source platform. I hope that some of you will look at it. But so the roof is there as a neon billboard sign. It says like, look at me. But the reason that I'm excited that people are looking at it is because of the floors. There's something special about the floors. You can't see it too much in this picture, but they're 3D curved. So they have this vaulted geometry. So let's maybe look at this floor. But first, I want to sketch a little bit why I am increasingly excited in this presentation that I can get to show you our floor developments. So this is how many floors are being constructed in concrete all over the world. But what is really interesting is that if you look at the medium high rises, so 10 to 30 stories high, very typical typology in densified urban areas, then you see this absolutely absurd situation that 3/4 of the mass of those buildings is in the structure. So as a structural designer, I am very frustrated by these kind of things, because it suggests indeed that the structure is mainly there to keep itself up. If you then zoom in a bit more, then you see that more than half of that structural mass is in the floors. So spanning space is really the bottleneck, is the most material intensive component. Very banal, we all need a floor to walk on. That is the element where we really need to disrupt. And that is what we are now trying to do with our research. We talked about this 1 New York City every month for the next 40 years. Another calculation is that in that same time frame, we will be building more than 200 billion square meters of floor area, which translates to more than 2 trillion square feet, right? So this is quite a challenge, or another way, this is quite a business case. So let's now talk a little bit about material effectiveness, because maybe many of you are still listening to me with a bit of skepticism. Why is he talking about sustainable achievements and he's only talking about concrete? Well, all of us seem to agree that concrete is the most destructive material on Earth. Well, yes, but is this statement by itself really appropriate? And again, it relates to the fact that it is not just a material problem. And so we have very good proof for this. So if you look at concrete, the embodied energy per unit mass, or on the right, the embodied carbon coefficient, you see that concrete is actually quite a good material. The problem is how we are using concrete inappropriately in geometries that it doesn't want to be, and so on. You see, the only material that we can absolutely not beat is sustainably sourced timber. So let's question what it means to source timber sustainably at the scale that is needed for urbanization and growth. What does it mean to really have sustainability in timber? So that means that we cannot use engineered timber, because these components we will have to trash or incinerate at the end of their lifetime, and, right? So what I'm saying here is that we have this material that is readily available throughout the world. If we start to use this material in how it really wants to be used, probably we have a good strategy. It's probably obvious to you where I'm going with this. Artificial stone, that is what concrete is. These kind of geometries are really how concrete wants to be shaped. And by doing that, I focused on the volume before. but by not forcing concrete to be the flat slab because of that, you need so much more mass, you need so much reinforcement steel to force this material in a non-natural kind of geometry. So this is what we achieve. And that is then what we started to translate into 3D to be even more efficient. So the simple arch is now a 3D shell with stiffeners that accumulate to the corners. And that allows you to design, as an example, a 5 by 5 meter floor plate with only 3 centimeters of unreinforced concrete. And that, why I show you these numbers is that these are exactly the numbers of the HILO project. So there we have a fully approved, fully engineered, a real project that spans 5 by 5 meters with 3 centimeters of unreinforced concrete. So again, translated, we are talking about 16 by 16 feet with just over an inch of low strength concrete. And by the way, we use more than 50% of cement and aggregate replacement coming from construction demolition waste. Another opportunity when you indeed have very, very low stresses in the material. So this is not new, this story. We have been developing this for the last decade, literally. And in fact, next to the Armadillo Vault, similar idea that was shouting, look at me, we already presented one of those floors. And you see these nice stiffeners accumulated. An even earlier prototype from 2012, after cracking, you see how thin these geometries are indeed. And then we did many experiments. Another one was to use an equally weak material as the tiles in South Africa, right? So just 10, 15 times less compressive strength than a standard concrete, but absolutely no bending capacity. So we 3D printed this. This is Cent 3D printing. And we also showed this already in 2016. We did the entire American Concrete Institute's recommended loading protocol to demonstrate that the structure would be safe satisfying all loading conditions. But if this doesn't make sense, then maybe these 1,200 kilograms of ETH nerds, so a part of our research group at the time, standing on a 2 centimeter unreinforced structure with material properties equally comparable to cold dark chocolate. Perhaps this is more convincing. If you think that what I'm presenting is totally disconnected of modern practice, if it is academic, is naive and so on, oops. I was preparing for a slide. I didn't see my next slide, so I'll skip that one. But let's actually see, let's actually look at the impact. So if we go beyond this one element and we look at any of these towers, right? So this is a picture, for example, in China. Any of these towers, we did a simple calculation to see what would happen if we would replace a standard optimized concrete floor slab with our system. So let's take a 25-story building and let's see what happens. Of course, what we're using is on the left that more than 40% of the mass will be in the floors, and on the right, the savings that we can achieve. Obviously, you're paying attention and wondering why this doesn't say 70% and 90%. That is because the HILO floor needed to satisfy a 30-minute fire rating, and this is fully engineered for a 90-minute fire rating. And so you need a bit of compensation to deal with these increased fire resistance demands. And so that is why we had to correct the numbers a bit. So, but if you use these numbers for this one building of 25 stories, you would save more than 7,500 cubic meters or 9,800 cubic yards of concrete, less for that one building, which translates to 1,200 concrete trucks that would not have to go to this building site. But additionally, you would save more than 14 miles of number 4 reinforcement steel per floor. Or if you were to roll this out, it's like, and this is a nice coincidence, it's like going from Zurich, where I live and work, to Brussels, where I'm from. Or I did a quick calculation, it's equivalent to going from Miami to Orlando and back. That is how much reinforcement steel you would save for this one building. But that is not the only thing that matters. Again, I said that we should look at the real bottom line, which is the global warming potential. And a quick calculation there, I wanted to just break it down for you. By activating strength through geometry, we both get less volume, remember the armadillo fall, lower stresses, so that means lower emitting materials that is always going together. So you get both effects already. So that gives you already 3/4 of reduction. But then if you add a little bit of material innovation, and this is no longer innovation, this is quite standard practice, these green concretes that use fly ash, other kind of materials to reduce the problematic clinker ratio in your concrete, you see that you can get to just a fraction of the contribution of a concrete. If you then add the reinforcement steel, then we can provide a floor that has this number. If any of you are specialized in calculating these values, you will see that this is significantly lower than the state-of-the-art any timber solution that is around there, by the way. But that results to less than 15% compared to a traditional reinforced concrete floor slab. Maybe one thing that I wanted to say is because we are now developing this system for mass market. In fact, Holcim, our industry partner, has made a very public statement that by 2023, this system will be ready for the market for industrialized constructions. So every aspect needs to be checked, not just, obviously, not just structural. And a key challenge in lightweight construction is, of course, acoustics. But what is super exciting, and we have fully demonstrated this in high-low with professional kind of acoustical measurements, is that we achieve, rather than adding mass to deal with contact noises, with low frequency transmission noises, we activate structural stiffness, something that has never really been, or not to our knowledge, have been used really purposely in the built environment. So that means that in the worst case scenario, where we have the highest fire rating needed, so that would end up with less than 250 kilograms per square meter, we don't need to hit this minimal mass requirement. This requirement comes from the Eurocode. And so that means that we will always be lighter than systems that do not activate structural stiffness. And so I want to throw all of these criteria into the mix, because if we don't do that, we cannot have a nuanced, fair discourse about sustainability indeed. I quickly show you this, that it's exciting that we're working with many design teams in competitions and so on. The picture that I show you here is a 130-meter tower in Brussels that just was submitted with the approval of the city architect, where the funicular floor was from the beginning embraced, and where also very novel building systems were introduced to reduce the total height of the building, or offering more floors to the client. So a last thing that I want to say is that, like in the striatus bridge, we are developing this as, and sorry that I cannot show you, these are old images because there is IP involved and so on. We are really hoping to bring this to market very soon, but the general concept is the same, that we use fully reversible components using masonry logic, dry assembly, and all the advantages that I highlighted in the striatus bridge earlier. So it's a discretized system. If any of you are excited to already start planning this in, we can deliver. It's also economically equivalent to what we have on the market. So get in touch with me. This is exciting times to get involved and be first adopters indeed. Again, looking at this image and realizing that more than 40% of the mass of all these buildings is in this super banal floor plate, introducing an idea like what I just presented to you to address this issue could really get us a long way indeed. All right, I'll have to skip this, so apologies for that. I wanted to show what we're doing in South Africa. Similar kind of concepts. Maybe the key exciting things is that we have a floor system with low strength material that uses shredded invasive plants as aggregate replacements. So this is a final prototype before we built a demonstrator for the Department of Environmental Affairs in South Africa. Sorry that I ran out of time for this, because I want to still conclude. I talked about structural geometry to reduce mass. I talked about funicular forms, so compression-only geometries that result in very low stresses. So that means that we can use very low carbon footprint materials. So that allows us to significantly reduce the embodied carbon coefficient of the materials used. We use digital fabrication to try to reintroduce structural geometry without the associated excessive waste. So think, for example, of what we do in striatus, no molds, direct 3D printing. The concept of treating precast elements using the discrete masonry logic it gives you all these outlooks of circularity on many levels. And then I didn't talk about this too much, but none of them would be possible, meaning economically feasible, if you don't rethink how everyone collaborates, and if we don't find efficient ways to connect the design team to all the things that matter in fabrication on the construction site. So we need to integrate. We do this through computation, through Compass. We need to bring all of these different partners together. So with that, I'm at the end. Sorry that I went 4 minutes over my allotted time, but I would be very happy to get your questions, your comments, your skeptical feedbacks. I love those because it allows me to sharpen our research and to go further. But so thanks again for the invitation.
Thank you so much, Philip. Give me a moment to unmute. Great. Thank you so much. It's always wonderful to see your very qualitative and quantitative presentations. And I encourage everybody to visit Block Research Group's website and look at not only the projects, but also the software and teaching that's also incorporated with the work that you're doing. We have a few minutes left for questions, so I will try to translate if it's not loud enough, and then we're looking forward to your answer. Yes.
Yeah. I don't have a question. Well, I do have a question, but thank you so much for really inspiring work, exciting work. I wonder if you could also talk about, and this excites me most a lot because I'm working with natural ventilation strategies in buildings. I wonder if that undulating surface in the concrete also could increase the intake of thermal energy for example, nighttime cooling. Because it's always the surface, right? And it's not the mass of the concrete which provides storage capacity for heat.
Yeah, thanks for that question, and I like that you.
Were you able to?
Yes, I heard it. Yes, thank you. So the question is about one performance criteria, an important one that I, because I was rushing, didn't talk about, is indeed that the thermal activation opportunities that you have with a material like concrete. And like you say, indeed, the first 5 centimeters or maybe 7 centimeters is what really matters. And so that is what you can use for the 24-hour kind of passive heating and cooling, so that you use the coolness of the evening to ooze, to radiate during the day in the summer and things like that. So that is also actually something that we have noticed in, so this specific project in Brussels, in order for the client to want to accept that the design team would submit a project that is based on a system that is not on the market yet, the client asked actually the entire design team to develop 3 projects in parallel, like a typical hollow core floor plate, our system, the funicular system, and then a timber solution. And there, in fact, your question is directly relevant because the sustainability experts on the team, Drees and Sommer, excluded very early on the timber solution for such a tall building because the lack of thermal mass, the lack of the opportunity to actually use that would demand a total over-dimensioning of the building systems. And because the client didn't want to score only on the embodied emissions, but also, of course, want to be respectful towards operational emissions, this was a bottleneck issue when you go taller. And so that means that indeed, when you look at for example, a timber construction, If you just look at the construction, yes, then we might be doing not that bad. But if you start to indeed add the acoustical mass, add the thermal mass, and so on, then it's starting to skew the image a bit. And so, like you said, what's nice is that indeed the surface can also be treated to maybe radiate ideally in certain directions, and more specifically also in the HILO project, we use a low temperature gradient embedded hydronics that allow to kind of activate this thermal mass as well. So to do core activation at the same time. So that is indeed a nice opportunity as well of trying to finding exactly that sweet spot between squeezing everything out, but keeping just enough material and just enough geometry to achieve all these other targets, acoustics, like you said, thermal performance and so on. So thanks for that question, because I forgot to talk about it. Yeah.
Next. Yes.
Hi, thank you for your presentation. My question is more about the implication on the workers that have to install 3D print first and then install the structures. And in other words, I'm wondering if you are expecting, what you are expecting from this future worker using this new technology. They have to be highly skilled and trained to get into that level of installation, or what have you seen so far? For example, in Mexico City.
Yeah. No, thanks for that question as well. I mean, I must say there I am a little bit torn, because indeed we see on social media in company alerts, you see that, or messaging, you see that 3D printing is being suggested to kind of print entire schools and villages in a developing kind of world context. And there, of course, you have this very delicate compromise that you need to evaluate. What is most important? That there is 40,000 school buildings missing in Tanzania, for example, and that you want to produce and deliver them as fast as possible? Or is it more important to indeed offer bottom-up new economies, social economical benefits of activating local communities to build up their own schools and so on? So this is indeed a difficult question that we have to look at. But it also, I mean, the 3D printing, I have not proposed in a developing context, but we are indeed proposing this now in a more developed context, where indeed productivity is quite a challenge. It's not just an issue of hitting these ecological targets, but also providing fast enough all the infrastructure, or replacing the infrastructure and this housing that is needed. So maybe one thing that I want to, so I cannot conclude, or it's a delicate question. You're quite right that we need to reflect on this, on what the repercussion is indeed on the workforce. I don't think it's as easy as some of my colleagues in robotic 3D printing are arguing that, you take low-end jobs away and you provide high-skilled ones and you give up opportunities. It's not that simple. So I would not give that as an answer. But for example, we're lucky to work not only in our context, but also I show you some hints of our projects in an African context. But we are now also working with a developer in India to provide lowest cost housing solutions. And in order to be lowest cost, you need to squeeze out every single rupee, every single detail in the process. So in that context, again, there are two strategies. You can support through NGOs the opportunity of local communities to build up themselves. That is one way to offer a global picture of low-cost opportunities. Another one is to really try to, as I said, squeeze out every single thing that might be inefficient. And in such a context, developing a very simple 3D printing setup that allows you to make prefabricated components that still can be installed and finished and continued by workers on site. So that might be one of these hybrid forms where you try to address a bottleneck of mold making that might be too expensive, and that is maybe a potential outlook for 3D printing, is it might be actually the first disruptive technology that has the opportunity to offer opportunities to bottom-up initiatives rather than just the global players. What I want to say with that is that the investment in a pumping device, the investment in a robotic arm or a simplified robotic arm is so low compared to a prefabrication factory, compared to any construction kind of paradigm, that it might actually offer local people to innovate and to find solutions to go forward. So I don't have a clear answer yet because I'm myself struggling about actually finding the real value in a global context, but it's always also hard. I mean, every single context is different, and every single context needs to be identified. What are the opportunities? But so maybe if I could add to that, you saw also in the Mexico project that we only brought in the knit as an innovation. So I will never defend that we come in, we overrule all the local crafts and skills and opportunities, and we bring in robots that solve your problem, and then we go back out, right? And so I think it's more important than globally trying to answer your question, is to actually context per context try to identify the bottlenecks that make it inefficient productivity-wise, that cause unacceptable ecological pressures, that prevent solutions to be provided that are truly low cost and not just kind of supported by the government end to end. Sorry for avoiding your question a bit, but I think it's because it's a complex one.
Philippe, we're running a few minutes over schedule. Would it be okay to take maybe 2 more questions?
It's fine for me. I don't want to mess up your schedule. Yeah.
Thank you. I think there's many questions. Yeah. Okay.
So could you explain how you're dealing with seismic and lateral loading in the tower project?
Yeah. I am increasingly annoyed with myself that I don't proactively include this in my lectures, because this is typically, now it's question 4, but typically it's the first question that I get asked. So the nice thing is that and you see this also in history, through, for example, in Mexico City, these terrible earthquakes in the 80s, where most concrete construction buildings collapsed, and not these efficient shells from the past, even unreinforced brick vaults and so on. So that is on the element level, that actually we consider seismic indeed as a live load case like any other. We design for it, that all works. Probably your question is on the global level, that we of course cannot have a progressive collapse and so on. And that we actually, I mean, there's different strategies, but how we have been dealing with this, and specifically you asked about the tower project in Brussels, what we did is we basically make we just put sufficient redundancy in the frame structure around the infill panels to deal with all of that. So we allow different load paths. So for example, if a column goes out, then that column is hanging and things like that. So we do this by actually finding a clever way of the frame structure around it to solve the global stability. Other kind of challenges are, for example, the diaphragm action that is needed in the floor plates. So either you can take this directly in the floor plates, but that would demand an over-dimensioning, adding more reinforced concrete to, for example, have some compression struts that allow you to that diaphragm action. Another strategy is actually to have super efficient tensile cables in certain crosses, stiffening crosses in certain kind of fields in the tower. So that those are strategies that we've used in this tower. So it's not being ignored, obviously not, but it's used in a slightly different way. But globally, it all works out. With that, though, to be specific about your question, the things that I showed now and what we are developing as a first target are not proven yet, or have not been tested yet, or have not been developed for California, for Chile, for Turkey, right? So for heavy seismic regions, there is no fundamental thing that would not work, but we will not deploy it there in a first stage. So we can only cover like 85% of the world for now with these systems. But so just to summarize my answer, yes, on an element level, seismic is taken as any live load case, but then you do have some additional requirements on the framing around the elements to deal with seismicity. Yeah. So thanks for your question. I should put that in my lecture. It's so annoying that I ignore this always in my excitement of focusing on the sustainability targets. Yeah. But thanks for the question.
And one last question. Go ahead. If you could speak up. Perhaps a little bit, yeah. Or I could repeat.
Congratulate for your work, your presentation, and maybe giving you a suggestion from an architectural point of view, we should be adding a more, let's say, aesthetical advantage of your work, because I think that as humans, we need a beautiful environment, and the beauty of these structures coming from the forces that they, are revealed against the flatness of, our doors or walls, it actually helps even, the wellness, the well-being of people by being in a beautiful environment.
Yeah.
And this will also help architecture and engineer go back together after the big separation. And it reminds me the work of Philippe. That could be a good example for even Gaudi, I would say, but again, I would say that the beauty of the structure itself has been hidden under these floors and under this flat.
Yeah.
So I think that you should add a more aesthetical pleasure to your work.
Yeah. Yeah. Thanks a lot for. Oh, thanks a lot for that comment. And yes, I mean, I would agree with you that there is an inherent, almost natural aesthetic that comes by really following constraints of fabrication of structure, and that you feel that, and that could be celebrated more. I am careful with actually suggesting a certain style that dictates this need, right? So I focus. I mean, of course, I enjoy this, and and for me, those are beautiful forms, and we know this also that it appeals to the colleagues that we team up with, that want to use these forms also as a unique opportunity to also achieve architectural quality. But I'm very careful in the most extreme way, then indeed you need to show what the structure is, how the fabrication, and so on. And I like that tectonic kind of quality. But I think we would be missing a large percentage of audience if we would insist that is an aesthetic that needs to go together with the solutions. So, for example, I am actually also secretly a little bit looking forward to an architecture team or a collaborator that wants the efficiency of the system, but then clads it entirely. And so, for example, with a hanging ceiling or something like that. I know it's a bit perverse what I'm saying, and it goes against what I've been presenting, but just to show that these vaulted or non-standard geometries are not a necessity. So there's two aspects, right? I mean, so you have a gradient of what you can achieve, and I am real or realistic enough to realize that if you start to impose an aesthetic together with an optimization opportunity, that you're going to miss out in a lot of impact. So I'm much more pragmatic than that, but I agree with you that there is something to be said about a reintroduction of an integrated aesthetic that achieves architectural quality by celebrating or understanding the structural and the fabrication kind of constraints, and this of course depends also on different materials. I gave you an example. I gave you our trajectory, our development in concrete, but you can imagine similar kind of aesthetics, similar kind of logics that make sense for timber, for earth and construction, and right? And so I think that is more important. But thanks for the comment. I fully agree that at the end of the day, we also need to make beautiful structures. That is also very important in sustainability. It cannot just be over-engineered, optimized kind of systems. We need to be happy where we live. And some people argue that natural curves make you happier than flat boxes that we live in today. So, but I'll leave that to whoever takes on these kind of concepts.
You said beautiful, functional, and structural. That was the 2,000 years ago, it was said. So I think that you shouldn't be too, ashamed or careful about saying so, because really your brain needs beauty to be well. So it's invited, it's naturally inherent in the structure that I'm not saying aesthetics by,
No, I think unless I don't hear you well, but I think we're talking about the same thing. I just want to warn that imposing a certain, it doesn't matter. Yes, thanks.
Okay, so I want to maybe just highlight that actually in 2016, where the Armadillo vault was presented in Venice Biennale, due to fabrication constraints, the pattern that was introduced was extremely tactile. So I think that project was a project that really brought aesthetics and fabrication necessities together. And I remember being in that room, and everybody was not only fascinated with the scale, but actually they were experiencing through touch this kind of the force field that was created. So there's definitely attempt there. But with that, I want to really thank you, Philippe, for sharing your time, the incredible research, and your approach to, in this case, topic of the conference, which is resiliency. So I'm sure there's many questions, but hopefully you'll be in touch to perhaps to collaborate in the future, and we hope to host you in Miami in the near future. Thank you so much again, and
thanks everyone. Have a very nice symposium, and see you soon, hopefully indeed. Ciao.